ZK-Rollups don't just need valid computations. They also need transaction data that users can access. Without that data, users can't rebuild state or safely exit. In this section, we'll connect data availability to security, decentralization, cost, and real product design. So far, we've moved from scaling pressure to Ethereum settlement to rollups, ZK proofs, and transaction flow. Now we turn to the next question. What data must be available for users to verify or recover the rollup state? The rollup proof can say, this calculation was valid. Data availability asks a different question. Can users see the inputs behind that calculation? Without those inputs, they cannot independently check balances, exits, or the latest state. Validity proofs answer whether the rollup state transition was computed correctly. That is essential, but it is not the whole security story. Users also need the underlying data so they can reconstruct balances, monitor changes, and prove what they are owed. If an operator withholds that data, the proof may still verify, but users may not be able to exit safely. Correctness protects the rules. Data availability protects recoverability. State reconstruction means anyone can rebuild the rollup's latest state from published data, apply the agreed transition rules, and check the resulting proof or state root. This gives users a way out of blind trust. Wallets, explorers, and watchdogs can independently confirm balances, transaction results, and inconsistencies. If a sequencer goes offline, available data still supports coordination, recovery, or exits, because ownership can be proven without depending on one operator's interface. Here's the failure mode. An operator submits a batch, and the proof checks out, but the transaction data behind it is withheld. Cryptographically, the update may look valid. Practically, users are stuck. They cannot recompute balances. Auditors cannot verify the state independently, and anyone trying to exit may lack the latest ownership proof. Data availability is not optional plumbing. Without it, a system can be formally valid while becoming unsafe to use. In the rollup lifecycle, data availability matters once transactions have been ordered into a batch. The prover creates a validity proof showing that the state transition is correct, and Ethereum can verify that proof. But verification alone does not guarantee that users can see the transaction data behind the result. That data, or a compressed version of it, must be published somewhere. On Ethereum, through a data availability committee, or on an external DA layer. The strongest model is to publish the data needed to rebuild state directly to Ethereum. That data may be posted as calldata or, increasingly, as blob data. The benefit is trust minimization. Users rely on Ethereum's security and censorship resistance, and properly equipped nodes can retrieve the data and verify the rollup. The trade-off is cost. Ethereum block space is scarce, so publishing data there can become expensive when demand is high. Another approach is to move availability off-chain. This can reduce gas costs and improve throughput, because the system is not paying Ethereum to store every required data blob. But the guarantee changes. A committee, operator set, or external provider may attest that the data exists. Users then depend on those parties not withholding it or coordinating dishonestly. In short, cheaper data, but weaker recovery and less trust-minimized security. Specialized data availability layers focus on one job: publishing and serving transaction data. Rollups or app chains can use them while keeping execution and settlement elsewhere. Techniques like erasure coding and data availability sampling allow many nodes to check that data exists without downloading everything. The trade-off is still security. Costs and throughput may improve, but trust shifts to that DA network's validators, economics, maturity, and decentralization. There is no single best data availability model for every rollup. Publishing directly to Ethereum gives the strongest recovery guarantees, but usually at the highest cost. Committees reduce cost by asking a smaller group to attest that data exists, which adds trust. Specialized DA layers target higher throughput and lower fees, with separate protocol risk. User-focused committees may improve privacy or UX. The right choice depends on asset value, user risk, and recovery needs. A validium keeps the ZK-Rollup idea of proving correctness, but changes where the data lives. Ethereum receives validity proofs, so invalid state transitions should be rejected. However, the transaction data needed to reconstruct state is stored off-chain. That can make validiums cheaper and faster, especially for high-volume applications. The trade-off is availability. Users must trust a committee or external provider to keep the data accessible when they need it. Volitions let one system offer two data availability choices. For high-value activity, users or applications can choose on-chain data and pay more for stronger recovery guarantees. For lower value or frequent actions, they can choose off-chain data and accept extra assumptions for lower cost. The trade-off is flexibility versus clarity. If users do not understand which mode protects which assets, the system can appear safer than it really is. When reviewing a rollup, don't stop at "there is a validity proof." Ask what data the proof depends on, where that data is published, and whether users can retrieve it without permission. Then test the recovery path. Can a normal user reconstruct state and exit if operators disappear or censor them? Finally, match the data availability model to the risk. A game may tolerate weaker assumptions. High-value finance usually needs stronger, more transparent guarantees. The core distinction is simple. ZK proofs show that transitions are correct, while data availability lets users verify, reconstruct, and stay safe. Ethereum DA maximizes trustlessness at higher cost. Off-chain DA lowers cost, but adds assumptions. Validiums and volitions sit along that spectrum, which leads naturally into the broader trade-offs every rollup design has to make.